All right. Okay, so today we actually finally get into talking about some of these time series models. And as you can see here, I listed all of the different models. This is not even all of them, but what I wanted to note here, and we'll see as we go through the models, is time series modeling, and I will say traditional time series modeling, which includes all of these, is very modular. So basically each of these letters or each of these like groups of letters represents a different part of your model that you can incorporate or not, depending on your data. I've also linked this. I like this cheat sheet a lot. I think I sent it out to you all yesterday, but this just gives you like a quick rundown of like the code for implementing each one. And if you look through these based on whatever you want to implement in your time series model, you'll see that they're all very, very similar. But some of the main ones that we'll be talking about, and you'll see they kind of build off of each other. We'll start by talking about autoregressive models, and that's the first one, as you can see here. We'll talk about moving average models. You can basically combine both of these, make an Arima model. You can include differencing, and we talked about differencing yesterday, to make an Arima model. So the I actually stands for differencing, and there's a little bit of information why differencing is an I. With Sarima, the S stands for seasonal. Anything with an X stands for exogenous variables. So as you've seen yesterday, when we were predicting the price of shampoo bottles, we only use previous prices of shampoo bottles to, or shampoo sales, previous numbers of shampoo sales to predict future shampoo sales. Exogenous variables, and we'll talk about that later, is just including other factors in your model. Like for example, what about soap sales? That is an example of an exogenous variable that you can actually incorporate into here. And then Saramax, I would say, is like the most complete one if you want to incorporate all of those. Saramax is seasonal Arima with your exogenous variables. And you'll see that it's really very additive. It's modular, and you can basically include whatever you want to include in your time series model. So questions before we get started? All right, so the first one we're going to start with is an AR model, so autoregression. And as a quick recap, autoregression is when a time series is correlated with itself a couple lags back. So basically, an autoregression model makes the assumption that observations at previous time steps are useful to predict the value at the next time step. It's one of the simplest time series models because we're really just using, you can see here the prediction for T is equal to some coefficient multiplied by yesterday's price and some error term. So yeah, the one denotes that the next instance is solely dependent on the previous instance. That's usually when you have AR1. I don't know. Yeah, AR1 just means that the next instance is solely dependent on the previous instance. And this, again, is a coefficient. Very, very similar to linear regression. As you can see here, it's actually a linear model because you're multiplying your variable, the variable being yesterday's price, by a coefficient. And this you can sort of think of as like a constant term. So with autoregressive, you can actually have multiple lag terms. So you can predict price using yesterday's price and 2 days ago's price. And I actually have examples showing that in a little bit as well. So yeah, how do we determine?
Is that the concept of like order when we're talking about like when you have to fill in the order, like the P and the Q?
Yes, yep, that's right.
So that would be if I had a lag or I wanted to include information on shampoo prices for my AR model from like the last, 40 days, I would have a
AR40.
AR40?
Mm-hmm.
Okay.
Yeah, and there's actually a printout that's very similar to the stats models linear algebra printout, linear regression printout that I'll show you on. We'll dissect that a little bit too. So yeah, you're welcome. So with deciding how many lag terms you use, as I mentioned yesterday, you can use your ACF and PACF diagrams to determine, all right, which time period and which lags are autocorrelated with your time series. I will also show you, or I'll talk about a method later that there's like a quick way of like doing grid search for these kinds of models that I'll mention in a little bit as well. So you don't have to like test all of them, because sometimes it is a little ambiguous what number to use. So importing the libraries we're going to use, these are the usuals. Here we're actually going to use root mean squared error to evaluate our time series model. And I'll show you how we do that in a little bit. And then here I'm actually importing Arima. And Arima, we're only starting with AR, but because it's modular, you can actually use Arima to do AR modeling. And I think as we see some examples, it'll make more sense. But we're going to use the same CSV as we did yesterday, the shampoo sales. And this is what it looks like, just so we remember. And then the first thing I'm going to talk about before we get into the models is train test split. So very uniquely for time series modeling, because the whole idea is forecasting, and forecasting being like, things that haven't happened yet. The way we do time series, because you can imagine with time, it becomes harder and harder to predict, right? Things could happen towards the end of your time frame that could completely change some of the underlying things that you've noticed in your data. So because of that, your train test split for time series data is done literally with some time split. So here, I mean, this is a small data set, so with bigger data sets, you have more flexibility in choosing what your time frame will be. But here I'm going to use my training data to be the first 2 years, and my testing data to be the last 1 year. And remember that this is monthly data, so I only have 24 data points in my train and 12 in my test. So take my results with a grain of salt, because it's not being trained on a lot. If you have something that is like, much more robust and much more granular, so let's say you have daily stock prices over the past like 20 years, it's not uncommon to train it on 19 years and then use your last year that you have in your data set as your test set, and then make forecasting predictions for like 2021, for example. Questions on the train test split? I will say there is a library that does the train test split for you rather than me manually putting the 24. I believe it's within scikit-learn. I think it's literally called time series split. So feel free to look that up if you're interested in using something that's more like pre-built. So before we get into the exact modeling, Arima, as I kind of alluded to up here, Arima is a combination of autoregression, so the AR model, differencing, so the letter I stands for differencing, and I'll actually talk about that after this, and also moving average. So there's actually 3 components that you can include in your Arima model. But first, we're going to start with AR models. So the way that AR models work, or the way that Arima models work, is you actually have to give it 3 different arguments that come within the order. So it's the letters that represent these are P, D, and Q. Why they're called P, D, and Q, why it's P and Q, I'm honestly not too sure. But P basically is your autoregressive component. D is for the differencing, how many times are you going to difference your data? And Q is going to be a moving average that we'll talk about later too. So because we're just doing an AR model, differences and the moving average we're not going to consider for now. So you can see here, and this is the Arima model that I had imported over here. I'm feeding in my train set, and the order, I'm giving it a one-time lag for autoregression, and then differences and moving average, I'm going to leave at 0 to begin, because this is just an AR model. I'm fitting the data. The fit actually works like this. I know it looks different. I know in like scikit-learn, you actually put like your data here, but the syntax is different because this is stats models. The way that this model also works is if you just do .predict, it'll give you the predictions within your train set. And we'll look and see, I actually have a graph that will output what that is. And then if you want to predict time that isn't in your train set, so in my case, I have 12 data points in my test set, you actually can use the forecast method to forecast however many points you want. So let's just run this really quickly. My model has been trained. I have my preds for my train and test set. And one thing we can look at is the summary. And I'll go through this in a little bit, but as you can see, stats models, pretty neat with this summary. And it looks very, very similar to our linear regression output. You can see here you have actually like your terms, and I'll go through these in a little bit. But just to see what this model looks like, here is just a graph of the predictions. As you can see, not doing super well yet. And then you can use your mean squared error to evaluate your train and your tests. So again, overfitting is still a problem in time series data. So it is important to take a look at your train RMSE. So basically this is the RMSE between like my points from 0 through 24. And then my test RMSE, which I should have here, test RMSE, it's obviously bigger because we have not accounted for this upward trend. Basically how this AR orange line is being created, it is a linear model. You can see here, I didn't really explain this too much in depth, but it's really just taking the previous time step, multiplying it by some coefficient with some constant term. And that's exactly what we're seeing in the output here. You can see here we have our constant term, we have our AR term, our autoregressive term. So basically this component says that, you know, for the next time step, we're going to take yesterday's sales of shampoo, multiply by 0.24. And then this sigma 2, I believe, is some error term. But the most important part to note is this. Basically, like usually for each successive term, how much of the previous day's value is important. So with that, that's our first AR model. Any questions about this so far?
I'm just trying to follow along in the study group notebook, and there's an error running the model. And so it didn't run. It said some invalid value encountered in the data. I'm not sure what happened. Array must not contain infinities or nans.
Oh, okay. It might be. Is it in this step that it's breaking?
Yes.
There might be a nan value in the train set. So I know I think I ran into that issue with some of the later models if I have like different numbers here. So yeah, just honestly, you can just segment out. I think the nan value should be at either, it would probably be at the very end. So yeah, feel free to just segment that out. I'm not sure why that is occurring with the code that is in here. But yeah. Oh, something I forgot to mention as well. I actually just updated this notebook about an hour ago to include all of these code examples. So maybe that's an issue as well. So there are 2 versions of this notebook up on the repo. I believe I named it like updated. So that one is the exact version that I'm running currently.
Yeah, I fetched it right before, and so I have the updated one, but
okay,
it's not getting the error. So I'll just check for a nan value and see if I can get it to run.
Okay, sounds good. Thanks for letting me know. I'll like rerun everything later and see what the problem could be. Any other?
So kind of going through the study group materials, they used like I think AIC and BIC as their metric of like which model was the best fit. So should we be using that, or do we want to be looking at our MSE?
So both. So AIC and BIC, as you mentioned, like determine best fit, right? And remember, this is something that we also talked about with like, actually in like phase 2 and phase 3, best fit doesn't mean that it's the best at predicting. So you definitely want to evaluate both. So you can sort of think of AIC and BIC like your kind of like your R squared, and then your RMSE to determine like, you know, the predictability of your model.
Right, okay.
Yeah, that's a good thing to bring up. Anything else? All right, we're going to keep building on this. This was an AR1 model, and AR1 just means with one autoregressive term. Our next model, we're just going to see what happens if we add another autoregressive term. So here, you can see here, I changed my order to be 2 for autoregression, and we're just going to go through all of the same steps. Let me just change this. AR2. All right, so the main thing I wanted you all to see with this AR2 model is when we have an order of 2 here, we are actually considering 2 time steps before us. So we are taking one lag term and a second lag term, and your current prediction is going to be a combination of the 2. So take that into account. yeah, so with that, let's take a look and see what our graph looks like. Maybe a little better. Let's take a look at the results. You can see our test RMSE is 257, where before it was 269. So a little bit better. But just remember that these two models, we're only using 2 days back data points to predict today's data points.
Can you explain the graph when you say it looks a little bit better? What do you mean? What are we looking for? I don't get what we're looking for here.
Oh, yeah. So the blue line is our original data of our shampoo sales monthly, of our monthly shampoo sales. The orange line is the results from our model. So literally this orange line at for example, this point here at day 3, it's going to use some fraction of day 1 plus some fraction of day 2 to end up at day 3's price. Does that help? And then this is just going to continue on the same calculation throughout like the 36 days.
So are we looking for the orange line to match the blue line, or what?
Yes, we want the orange line to match the blue line. If the orange line matches the blue line, that just means that our model is fitting the data better. And just keep in mind, similar to like a linear regression, the only 2 features we're using is data from the day before and data from 2 days before. And the fact that you can get like a line that somewhat seems to be following, at least like in terms of the direction of how it's moving, it's somewhat following for like the most part, especially in this region. I think it's pretty good. The fact that we're only using like some component of, the results from the day before, from yesterday and the day before. Compare this to this. Yeah, they kind of look similar for now, but we're going to keep adding different kinds of terms to our model to build on it. Does that help?
Mm-hmm.
All right. Sounds good. So yeah, this is an AR model that's only using, the data from 2 days back. Something that I wanted to mention, I'm going to talk about like moving averages and differencing. The implementation of the model is exactly the same. This is the same code that you're going to be using for all you're doing is you're going to be changing your differencing and your moving average amounts.
Excuse me, Ish. I have a clarifying question. At the end of the orange line, this is our prediction?
Yes.
Flat?
That's right. So anything that's after 24 is going to be a prediction from the model, because this data before, like 24 and before, that's the data that it's being trained on. And then 24 and after, it's just forecasting. Oh, something else to mention is that this model, so let's say you're making a prediction for day 3, and you can already see that in day 3, I'm not sure exactly which one day 3 is, but let's assume this is day 3. In day 3, and let me just zoom in and annotate. So in day 3, there's a little bit of error. I mean, there is definitely an error like between here and here, right? That is the error in our prediction. This model doesn't take into account this error yet. So this model is just going to keep building on, all right, I saw this price, I saw this price, we're just going to use these to predict this. It's not going to take into account like, all right, this was wrong, this was less wrong to use this. So it's not updating its information as the days go by, if that makes sense.
So it doesn't consider the trend in our prediction?
It does not.
Okay, thank you.
You're welcome. Anything else before we move on to adding other terms? All right, and when I say adding other terms, I literally mean adding other terms. So all of these models that we're talking about are going to have a very, very similar format to this and very similar to our linear regression model, that we're just going to keep adding autoregressive terms, moving average terms, and differencing, not really, but yeah, we'll see. We'll see when we get there. Okay, so we've talked about AR models. Now moving average models, including a moving average term, sort of accounts for overall trends. And a good thing is that moving average terms do consider your past errors. So we'll see here, sometimes a past value is not a useful indicator of what value will come next. If you find that your data is very, very sporadic and has no autocorrelation with each other, that's a situation in which, you know, past value is not indicative of what will come next. So yeah, consider a system that's subject to a lot of shocks and volatility. For example, Bitcoin price. There is no way that people could have predicted this like recent weird surge in Bitcoin prices. If a previous time period experiences a shock, it may cause an error for future predictions if we just use that value. And a moving average model helps to address this behavior. So a moving average term in a time series model is a past error multiplied by some coefficient. So we'll see here you have some average. Again, this is your constant. And what we're adding on here is, I forget which part is which, but I believe this is the coefficient and this is the error in your prediction the last time point. So this model, and remember before I talked about with this model, you know, it's not going to take into account how off the predictions were in previous steps. With a moving average term, you actually do consider the errors. So fitting the model, we'll actually get into an example after we talk about differencing. But if you want to include moving averages in your model, all you have to do is update, where is the code that has the PVQ? Here, sorry. All you have to do is update your Q, this number, and it can be any integer, which is basically how many past error terms you want to take into consideration with your model. Questions about that part so far? All right, so we're really just building on an error model. You can have a moving average model by itself. So then if it's just a moving average, this number would be 0. And then this would be like your 1, 2, 3, depending on how many past error terms you want to incorporate. And that will be your moving average model. I just think it's easier to use, well, at least for this purpose, as we're iterating through different models, it's useful to just use the Arima syntax. But if you're curious, this link actually has the specific syntax for just a moving average model, I think. Oh, yeah, you see here they're also using Arima, but here they are using like a plain autoregression model, but it gives you the exact same result if you're using this or the Arima model with the I and the MA being 0.
I think, so I don't think I understand how it takes into account past error terms. Like a moving average, wouldn't that just be like taking an average of like a window and then including that in your prediction, or no?
Kind of. You can sort of think as like of moving average as if, you know, so the way that these models works is looking at your data points sequentially in a way, right? So as you're generating predictions, you can look back and see how off your prediction was and then correct for that. So I guess it's not really like you're taking a window and taking the average. I know that is traditionally what a moving average is in like finance terms, but here, I'm guessing like the average comes in when you're just trying to like regress your predictions closer to an average value, if that makes sense.
Okay, so it's really just trying to correct for the previous errors.
Yeah, okay. Literally just that. So let's say if you find that in your past 2 predictions, you've been under predicting, your next prediction will account for that and move your predictions upwards.
Okay.
So, I mean, there is going to be a lag in like, you know, your catch up from your predictions and your actual data. But yeah, the aim is to account for past errors. And typically with these models, if, you know, you get from something that's more sporadic, your predictions typically in like in a time series that is more, wait, what's the word I'm trying to come up with? Basically, if you have a time series that is fairly stable, if you're introducing moving averages, your predictions will over time get more and more accurate as the errors get smaller.
Okay.
Yeah. But of course, in real life, you don't have very stable time series data. All right, so after moving average, we come back to talk about differencing. And yesterday, remember, differencing is what we use to account for upward, downward trends So differencing is something that isn't really a term that is being used in the linear regression model. It's kind of like a step that you do pre-fitting the linear model. And so as what we talked about yesterday, and I have an example that actually, let me just print this out first. With our shampoo example, you can see here, this is without differencing, this is differenced once, this is differenced twice. The first level of differencing kind of like flattens it out, right? So we're losing that upward trend. And if we difference it one more time, you can see that it kind of gets flatter. So if we actually were to difference it one more time, overall, if you keep differencing your data will converge to a straight line. And so differencing makes it easier for a model to detect patterns because it takes away that like upward or downward element. So yeah, questions about this so far? Okay, so this is literally the same thing as what we had. If we have a differencing by one period, you can see that each new time period is just gonna be the difference between today and the last day. And if we're doing that again, we're doing this difference minus the difference between yesterday and the day before, which is why we end up with this like kind of quadratic equation looking thing. All right, and with differencing, with differencing and with moving averages, we can combine all of them to create an Arima model. I know that this looks pretty intense, but it's actually pretty simple when you break it down. So Arima combines our autoregression, our differencing, and our moving average. We talked about this already. The reason why we use a letter I is because a time series which needs to be differenced to be made stationary is said to be an integrated time series. So the I actually stands for integrated. So to break this up, this part, the one that has like the y t minus 1, t minus 2, this again is a linear equation. You can see that like each term between all the pluses is just some coefficient multiplied by some value. So these are all our autoregressive terms. Anything that is multiplied by, itself in previous time periods, these are all autoregressive terms. And then these will be your moving average terms. So you can see here, we're considering the error. Oh, this is also autoregressive, so because it has the y. But here we're considering the errors from one time period ago, from 2 time periods ago to like however many. So the number of terms that we are including in our linear model, that's how that changes as we change like the order in our Arima. So for example, like the number that you put for P literally will be the number of terms that you have here. And the number that you put for Q is the number of terms that you put in here. And then D is something that you figure out as you test the different differencing orders. Questions so far? All right. So yesterday I mentioned the Dickey-Fuller test, and remember that the Dickey-Fuller test is something to test for stationarity. So let's just quickly test to see if our data is stationary. Here it's actually called import AD Fuller, and all we have to do is just feed in our data to see if it's stationary or not. From this, and again, because the test results are a little weird, I'll show you in a little bit. Oh no, why is it a NaN value? Let's see what happened. That could be Melody why yours is also running into issues. Let me just take a look and see what shampoo is looking like. Is there a NaN value? That's weird.
Yeah, I checked the train and test and I didn't see a NaN value. So
yeah.
I couldn't figure out why I was doing that.
Weird. Okay, I'm not too sure what's going on here, to be honest. I literally ran it right before this and it was fine. Let's take a look and see what this gives us. All right, so here we do have our values here. Basically, this and what I meant to do here is to like coerce that into a data frame so it's a little easier to read. But if you look up the AD Fuller documentation, it'll tell you that this is your test statistic. This is the p-value, the number of lags used to calculate your stationarity, number of observations you have, and these are your p-values at different critical values. So typically we want to look at our 5%. We want to look at our 5% p-value, which right now is 2.98, which is, let me just see really quickly why this is the case. Oh, I think I know why. I think this might fix it. There we go. All right, our p-value ends up being 1. I forget how we pulled this up. Anyways, our p-value ends up being 1. And I mean, we could tell through like the shampoo trend that this is not going to be stationary. So our p-value being 1 means that we failed to reject the null hypothesis that our data is, this data is not stationary. So what I'm going to do here is I'm going to difference the data once. And I know I just forgot to change the variables. But after we difference it one time, you can see that our p-value goes down to a pretty small decimal, like the 0.10 of a decimal. And so we can assume that, all right, with one difference, differencing our data once makes it stationary enough. Questions about this? I know there's a little bit of a, yeah, but questions about this?
Sorry, are those critical values negative?
Critical values, which critical values? The
ones that we saw that was like at 5%.
Let's take a look. There we go. These, yeah, I believe these should be the critical values on both sides.
Okay.
It would be doing like something similar to a t-test. And then if we take a look at the difference, we'll see that the p-values are, maybe that isn't the p-value. Oh, this is the critical value, sorry. This is the critical value, and then this is your p-value.
Right, so if you have that first, that first test statistic that's less than the 5%, then it's gonna be a p-value that would be lower.
Yeah, that's right.
Right, okay.
Yeah. Other questions about this? All right. Well, before we get into finally implementing, let's just take a look at our autocorrelation, because previously we were just doing it with like a quick assumption of however many. So here you can see that this is our autocorrelation. So you can see that there is some autocorrelation that does persist. And when you have persisting autocorrelation, we do the partial autocorrelation. And again, autocorrelation, this literally means that, all right, if we were to take the time series and compare it with one lag, it has like about a 0.73 correlation with itself. 2 time lags, about a 0.75 correlation with itself. And yeah, partial autocorrelation does this, but discounts the previous autocorrelation. So from this, it looks kind of like ambiguous whether you want to include 1 or 2 terms, and that's something that we can test for sure. So with the Arima, now we can fit in parameters for P, D, and Q. So let's just assume we're going to include 2 autoregressive terms for now, since you can see that like for the next 2 steps, there is some correlation with itself. Let's just do one differencing, just because the Dickey-Fuller test said that after one round of differencing, it's pretty stationary already. And then let's just include 1 moving average term to account for errors 1 period back. Same procedure. You can see that I'm doing the dot fit here. This I'm really just doing for the plotting because I want to include 2 terms to begin with. In the graph, I'll show you why I did that in a little bit. But what I wanted to show you all in this dot summary page is here we have the 2 autoregressive terms with our coefficient, as well as a moving average term. So these would basically be like, if you were to write out your linear model for your time series, it would be these coefficients multiplied by, you know, this data from like 1 day back, 2 days back, 1 day back error. What the roots are, not important for now. It gets into like imaginary numbers, and I know that sounds crazy, but yeah. All right. So the reason why I'm doing this, where I'm really just like adding 2 zeros at the start of my predictions, is because to make these predictions, the first couple of days have no predictions, right? Because we're including up to 2 days back of data in trying to predict the next day. So if you only have 1 day of data, you can't really make a prediction. So I actually just have it as a 0 to start. So we look at our train preds, you can see that I started at 0 just so I have 24 data points on my graph. So we plot the graph. You can see here, based on this, these are what our predictions look like. Which I feel like at least it follows the shape of like this increase up here. And because there is a moving average term, your data sort of learns where it's off and therefore tends to converge, especially if you have like ongoing trends. Let's just take a look at our, yeah.
The differencing term, because it's supposed to account for trends, basically like told the orange line that it's like an overall upwards trend.
Yeah, in a way, yes.
So that the line can account for that. Okay.
Yeah. The thing is that there are multiple things at play here. Let's see what this is. Let's do this and see whether, just so we can get a number real quick. You can see that our train and test RMSE are closer, which is good. But I believe that, I think this RMSE is lower. Let's take a look. 100 and, yeah, from 257 to like 100 and something. So this is just including multiple terms into our data. Yep.
Got it.
Any other questions? All right, so this is the Arima model. I will say like the main parts of traditional time series models are the Arima, the 3 PD and Q terms. Something that I guess I like mentioned it earlier is, what if it's kind of ambiguous on like how many moving average terms to include, how many AR terms to include? With differencing, you could argue the more you difference, the better it would be, because the more stationary your data becomes. So what is like a good number to choose? Honestly, you could just try different numbers in your PD and Q and figure it out. Or I won't go through the code today, but I wanted to let you all know that it exists. Auto Arima does exist. And Auto Arima is basically like doing grid search for your Arima model. And I'm not going to go through it, but I wanted to show you like the way that you set it up real quick. The way that you set it up here, let me zoom in as well. You can tell it like your minimum and maximum values for PD and Q to search through, and it's literally going to do like a grid search and tell you what the best PD and Q is to use. So if any of you are considering doing a time series model and it is a little bit ambiguous onto what values of PD and Q to use, you can definitely try Auto Arima. This article goes through the entire process of doing Auto Arima, but I will say, if you're choosing to do a time series product, you're not allowed to just do this. Definitely do some of the EDA, look for the differencing, look for the autocorrelation, just to confirm, at least, to confirm these values that are being output. But I wanted to let you all know that this does exist. Anything else before we talk about a couple other extensions? All right, so the next add-on to our Arima model would be exogenous variables, right? Like I mentioned earlier, predicting your shampoo sales, maybe with like soap sales, or maybe with something completely like, I don't know, like consumer goods sales overall. You can definitely include these in a model. I don't have the exact code here. Well, I do have this code here, but I don't have an example in this, but it's pretty easy to implement as well. So a couple of things to consider when you're including exogenous variables. So exogenous variables, Aramax extends Arima to include additional variables that might have an impact on what we are trying to forecast. Most commonly in like people who are doing like stock prediction projects, they include the price of other stocks. Maybe they include like bonds and like I don't know, yields, is that a thing? But they include other things in like, so you're not just using something by itself to predict, future prices or whatever. So things to keep in mind, does our exogenous variable actually impact our endogenous variable and not the other way around? So something that's important to remember, we talked about the idea of confounding variables with our previous projects. You definitely do not want to include variables that what you're trying to predict impacts. So sometimes it is a little ambiguous, and in those cases, there is a Grainger causality test. I believe it is within stats models as well. Again, you just have to look for a low p-value to kind of figure out whether it makes sense that the direction of causality, basically. Exogenous variables also have to be different at the same order as the endogenous variables. Just because, if you imagine, if you're trying to like flatten one trend, you would want to do the same with your exogenous variables, because if you are looking at the trend in the differences, you would have to do the same thing with your other variables, because those will end up being on different scales if you don't. By what I mean by different scales, you can take a look at, where did I have that? Oh, over here. You can see that this ranges from like, I don't know, about 100 to 700, because these numbers are the differences between each time period, the scale gets reduced, right? So here it's pretty much between like negative and positive 100. And then if we do that again, I guess it will slowly converge over time, but you can see here, you can kind of see that it is in a smaller range of numbers. So that's something to definitely consider. That's definitely something to consider if you're including exogenous variables. So with exogenous variables, you can sort of see here, this is Saramax, and I'll talk about seasonality in a little bit as well. But if you want to include exogenous data, all you have to do is when you import Saramax, which is what allows you to use exogenous variables, you literally feed in the column names or a data frame that consists of your exogenous variables. Of course, the number of rows has to match. So yeah, you can definitely just feed it in here and it'll take it all into account. When you print your output, on top of these, you'll see all your other variables in the same way as a linear regression. You're literally just fitting a linear regression at that point, if you discount these. I mean, these are also, they are also linear. So yeah, you're technically fitting a linear regression on itself. Any questions about exogenous variables?
Ish, that causality test that you mentioned, does that have other applications outside of time series data? Like, is it just a general function to understand like the causal relationship between two variables?
Yeah, it is. Yeah, you can use it. You can use it for, I guess, your last couple of projects as well.
Okay.
Yeah, but I will caution, because it is trying to do it mathematically. So definitely context will take precedence over this, if that makes sense. Like if you know the direction of causality and the Grainger causality test is telling you otherwise, I would use what you believe is right, rather than what the statistical test is telling you.
But it would tell you like not only are they just correlated, but there's like a causal relationship here as well.
Yeah, I forget the exact math behind it, but basically it's looking at like if you have like, let's say you have these shampoo sales over, oh, okay, well, this is airline passenger count. So let's say you have these airline passenger counts here. And let's say you have something else that is, I don't know, the safety, like the safety measure of planes, right? Like, I don't know how safe planes are, if there is something to measure that. So let's say your plane safety, and let's just like pretend they're on the same scale. If your plane safety thing is looking something like this, and you can see like basically the overall trend in passenger count follows after the red line increases, if that makes sense, then yeah, that's kind of what the Grainger causality test is looking for. Like what movement is influencing what movement, versus if like, I mean, I don't know what it is in real life, but imagine that like plane safety kind of lagged behind airline passenger counts, then the causality test will tell you that, all right, it seems that passenger counts is the one that's affecting plane safety.
Okay, gotcha. That makes sense.
Yeah, but it's something along those lines. I forget the exact math of how it's doing it, but yeah, something like that.
Okay, cool. Thank you.
Mm-hmm. Anything else? All right, well, the last thing that we want to talk about is seasonality. Seasonality is, I would say, one of the things that you should actually look for yourself. Just because, you know, the human construct of time, we've determined like weeks, months, years, for example. And if you have seasonality in your data, you want to tell your model to look out for that, to look out for repetitive patterns. So with these, order and seasonal order, you would use either this argument or this argument. So if you have no seasonality, you would just use this argument. If there was seasonality, you would actually just have this. The first three numbers are your PDQ, and then your seasonal order. The fourth number here will determine your seasonality, and that number is just dependent on, like, you know, how many periods are in a season. So for my data, let's just assume that like let's just use this data instead. So you can see that there are like constant like up and downs, and it seems like this is happening every year. And let's just say that this data is monthly data. So that means the season resets every month. So because it's monthly data, that means I have 12 data points per season. My number here would be 12. If it's daily, I put 365. So yeah, if it's weekly, I guess 50. I always forget how many weeks are in a year, but I think it's 52. So yeah, that is something that you can also incorporate. And yes, these numbers are the same, your PDQ. And then this will just take into account the repetitive patterns. And that is almost all of the traditional time series models. Something that I really want you all to recognize is that these are all linear models. They work in terms of like interpreting coefficients. It's very, very similar to the way that you interpret the coefficients in a linear regression model. So if you were to do a time series analysis, I would like to see some coefficient analysis to see that how much of, you know, the previous time periods are being considered. And yeah, I talked about auto Arima that you can talk about. I know that Ceramax actually only comes in the appendix, and I'm not even sure if they talk about exogenous variables, but here is a project walkthrough that I think will be helpful for those of you who want to explore time series. Any questions?
Is there any other function rather than linear regression in this regard? For example, a sine function that can calculate, for example, oscillation in different seasons or something like that, with different peaks in positive and negative points?
Oh, that's a really, really interesting thought, like using something like sine functions, because sine functions kind of match like the whole seasonal approach. In traditional time series, not that I'm aware of. I wouldn't be surprised if like some people have come up with, you know, trigonometrical models, but I am not aware of them. I'm actually, now that you asked, I'm very curious to know if there are, but I would say like in the class of traditional time series models, they are all linear. Whether they include like sine functions or cosine functions, not something that I'm aware of. I will also say that I'm less, like, I have not done as much research into time series myself, but I wouldn't be surprised if like a sine function or a model that includes like a sine term does exist. Something that is definitely worth checking out is the Facebook profit model. It's like in the appendix of time series, the Facebook profit model is actually very, very similar to a Ceramax model, just that it has, I don't know, they came up with something in their research to add further, what's the word? It basically is better at correcting prior errors. I also haven't looked into exactly why or exactly how they're doing it, but has proven to be better at making predictions compared to any of these traditional models. But again, as I think I mentioned this yesterday, with these traditional time series models, it is a trade-off between accuracy and predictions and also interpretability. So based on what you in your context value more, you might do these traditional models, you might level up to the Facebook profit models, or as we'll learn like towards the end of our neural networks next week, you could use a neural network as well for time series. But yeah, that is like a really like a 2-day overview on time series. I will say it's very compressed. Like I know in colleges, they spend like 2-3 weeks on time series data. So just be aware of that. Yeah, any questions to close out? For those of you who are wondering, the project on time series is actually predicting real estate prices for a zip code. And the way that they set up the project is actually really interesting. They actually give you a bunch of zip codes and a bunch of their price trends. And the whole question is framed around like, what are the best zip codes to invest in? So up to you if you want to take that challenge. You can also do it in a more traditional approach, like just predicting for one zip code. You definitely have that flexibility, but talk to me about it if you want to do something different than what is prescribed. Any final thoughts before we close out? All right, then. Tomorrow we start natural language processing, and NLP will continue till Friday, and then all of next week is going to be neural networks. And at the end of next week, which is so fast, we're going to introduce the phase 4 project. All right, if there's nothing else, I will see you all at your 101s, if not at study group tomorrow. Any questions as usual, feel free to Slack me. But yeah, have a good rest of your day, everybody. Bye.
Thank you.